So now we're going to go through a test example of running the PGSC calculator function, just the test demonstration that they give us in part of the documentation for the PGS catalog. And so we're going to run this on the DNA Nexus platform and see how that works. So yes, on the website, what they do is they show us, when we're getting started, that we are able to run this test profile, using Nextflow, PGS catalog, PGSC catalog, using this tool over here. And so we're just going to show, well, how does that apply for the DNA Nexus platform? Like, how can I just make sure that it's running smoothly and that, I'm able to get something to run and to work, and I have that infrastructure. So I'm just going to show you that example. And it's always recommended whenever you have or are trying out any new tool, hopefully they'll have some mini demo that you can work with, something simpler, just to make sure that it's working as it should, that there are no bugs. Hopefully. So this is just the first check, just to make sure that it's working properly for you so far. And then we're going to get more into the specifics. Yes, we will. So what does this look like for the DNA Nexus on the cloud portal? So this is a bash script that is designed to run on the DNA Nexus platform, which is a cloud-based genomics analysis environment where the UK Biobank data is. And the goal of this is to check that the tool PGS catalog calculator, it works in your environment. So what the first line is it's saying, okay, it's a bash script for us to run. So you can see it ends in a .sh. And this will create a multi-line command that will later be passed into the DNA Nexus Swiss Army knife app. I was always really obsessed with the Swiss Army knives. I think they're really cool. And they're very multifunctional, like so many things they can do. And this tool can do a lot of different things. So you'll see here that these are the different parts in the command. And we will run dx run Swiss Army knife. It's like the tool here. And then we have the command. This is the CMD that is going to be run here. So this is what each part will do. The first part here, this first line here, what it will do is it's going to download and install Nextflow, which is a workflow manager that is widely used in genomics. That's what the first line will do. The second line, this make dir /p, this local.bin, is going to ensure that the directory, this tilde /.local/bin exists where user binaries can live. Then this mv nextflow tilde /.local bin is going to move the downloaded Nextflow executable into this directory using this mv command. And so this mkdir is making the directory here, and then we're moving Nextflow there. And then this export path equals this area here. It's going to update the path so the system can find the Nextflow executable. So what we use this tilde $ path. It's escaped so that the variable expands later when the command actually runs inside the container. And then this last line here, this Nextflow run PGS catalog /PGSC_calc. This is the function. /profile test docker. It runs the PGSC calculator workflow from the PGS catalog GitHub repository. It uses the test profile, which is a small data set on Seneca, some data, and it uses a Docker profile so that it runs in a containerized environment. So that's what this command is doing here, in short. And then what we will do is we're going to run the command on DNA Nexus. So this will use the DNA Nexus Swiss Army knife app. Again, I think it's really cool, which allows you to run arbitrary shell commands in a controlled environment. And it has a lot of bioinformatics tools at its disposal. And we'll be using this tool, going forward for the rest of the examples here. It pretty much does a lot of things that we need. So this imd equals cmd command, it passes this command that I just went through into the application. The priority is high. It requests a higher scheduling priority on the cluster, and that will also make it a little bit more of an expensive job because we're trying to bump up its priority, and money talks. So if we want the high priority, we have it'll cost a little bit slightly higher to run this job. And the tag demo equals PGS calc here, PGSC calculator, this one here, it is going to tag the job with this demo PGSC calculator. So it's useful for tracking. We'll see that as we monitor this job on the DNA Nexus platform. And then this is the instance type here. I'm using memory 3 SSD1 version 2x4. So it just specifies the compute resources. So a virtual machine that has around 3 gigabytes memory and 4 cores. And I'll show you how we can check out the instance types. But this is what this command is doing. So in short, what this command is doing, this shell script is doing, is it's running inside the DNA Nexus platform. It installs Nextflow, runs the PGSC calculator test workflow, this tool using Docker, and ensures that it's all working correctly. And the computation is submitted via the Swiss Army knife app with specific resources and the priority. So that's what this code is trying to do in short. And we're going to run it using bash pgsc underscore calculator underscore test.sh, which I'll show you. So yeah, this is what it's going to do. We just have to write the bash pgsc underscore calculator underscore test.sh. That's the command we need to provide to the DX Toolkit terminal window. So now we're going to check that the PGSC calculator test demo works for us because even on the tutorial website, they mentioned to test it out and make sure that it's working. And that's what we're going to do right now. We're going to make sure that it's working for us. So what they do tell us is, as I was showing you, they were mentioning that we should run this command here. So I'm going to show you how we will do this in the DNA Nexus portal. So the first things first is that we're going to go to the folder that I created, which is in my desktop, as I was showing you here. We have this folder that I have, and I load this in Visual Studio Code, or basically just any place that you can use to access and open the code. So I've opened up Sanya demo over here, and I've gone to the PGSC, so the C stands for catalog, calculator test.sh. And so now what I'm going to do is I'm going to run this. So I'm going to run this over here, and to do that, as you see over here, we are in the DX login in our terminal. So we are already in the Sanya demo folder. So to see that, I can see that I have the PGS calculator test.sh. And so what I'm going to do is I'm just going to do bash. And we see that this is a bash file at the top. It has this beginning, and it's in .sh, it's a shell script. And so I'm going to do bash, and I'm going to type pg as calculator underscore test.sh, and I'm going to hit enter. Yes. So the job ID has launched. This is the ID of my job over here. So what I'm going to do is, now I have typed this here, and I'm going to go to the monitor. And then I had just clicked refresh. And then what I will see here is I will click on the Swiss Army knife here, and I'm going to see that this is the command that was registered in the DNA Nexus portal here. And these are the output files that we have here. We can see that these are all the different output files, including an aggregated scores.txt.gz, which will be the set of scores that we will use, that we get from this demo. So this just shows that what we get is, for instance, this is a file. We can download it if we like. And then I see over here that we get some scores for the Seneca example over here. And this is the denominator. That just means the number of variants times 2. And then we can look at the sum, which is what we will take. But this just shows us that the test demo example works, and that we do get something in return. So this is just how you will run the test demo for the PGS catalog calculator on the DNA Nexus portal. And that's just also an example of how you run a script using the DX toolkit here. We just did this bash command here. So this verifies that we are able to run the test example for this tool. Yay! So what is Nextflow? Well, Nextflow, it's a workflow manager. It's a framework for writing and running scientific data analysis pipelines. So when workflows become complex with tons of steps, large inputs, high performance clusters and cloud environments, it's hard to keep things reproducible, portable, and scalable. Just think of it like this. Normally you might glue together scripts like Bash, Python, R, Plink, and so on, with just some ad hoc shell scripts. I'm showing my example where I'm going through these 6 different steps, and that usually works for small tasks. But when workflows become complex, that's really hard, and Nextflow solves that. So we write our own analysis steps as small modules like processes, and we describe how data flows between them here. And Nextflow takes care of the execution by submitting the jobs, handling parallelization, and managing software environments, and resuming tests or runs even if they've failed, and so on. So that's really great, and just will keep on going. And why is it so widely used in bioinformatics? Well, I'll talk about the portability, reproducibility, parallelism, resumable, and community. So it's portable because it runs the same pipeline locally on a high-performance cluster or on cloud services, even like DNA Nexus, Amazon Web Services, without changing your code, Google Cloud Platform. So it supports different schedulers, Slim, LSF, SGE, Kubernetes, AWS Batch, reproducibility. So pipelines specify the exact software dependencies via Docker, Singularity, or Conda. And it's possible to reproduce the same results years later on a different system. For parallelism, it automatically parallelizes tasks when possible. So if you're doing the same thing for in our case for different scores, it will compute them in parallel. You just specify a bunch of score files, and it will handle the same task for each of the different score files, each of the different polygenic score traits. If you run an alignment step for 100 samples, Nextflow will launch 100 jobs in parallel. And if a job crashes halfway, it's resumable, so you don't have to restart everything. Just Nextflow run, resume, and it picks up from the failed step. And there are thousands of bioinformatics pipelines that are written in Nextflow. It's a community out there. Woo! The NF core community curates high-quality, peer-reviewed pipelines for common tasks, RNA sequencing, whole genome sequencing, metagenomics, and so on. And PGS Calc is one such Nextflow pipeline, and is written by the Polygenic Score catalog team. So how does Nextflow work under the hood? So Nextflow is written in Groovy, I kind of like Goofy, the Mickey Mouse character, very cute. But you don't need to know Groovy. It's a JVM language, based in Java. You just write small scripts in your language of choice and describe your inputs and your outputs. So Nextflow is a workflow manager. It's a pipeline engine, and it makes these complex bioinformatics pipelines portable, reproducible, and scalable. In PGS, catalog calculator tool, it is the engine that drives the PGSC calc pipeline. So you can see over here that we have, for instance, we've got an example mini workflow, thanks to, ChatGPT Insights as well. It shows its little example of a Nextflow pipeline here. So Nextflow figures out, it runs index genome first, this process, and then it runs a line reads, this process here. So once per input files read, input reads file, and then it parallelizes across samples if there are multiple FASTQ files that are involved. So you can just see this over here. Runs this process, and then it runs this. So yeah, we are not going to be writing a Nextflow workflow ourselves. That's not what we're going to do, but we're calling an existing Nextflow pipeline PGSC calc. And this pipeline knows how to take our, Plink genotype data or the formats that we've specified. There are 3 different current formats that PGSC calc supports, and a newer version would support more formats. And it knows how to, so it takes the genotype data, how to take a polygenic score file, with our weights, how to harmonize the alleles and variants, how to compute polygenic scores, and how to write out per sample scores. So for each of the individuals in our genotype data, each of those samples, what are their scores for that trait? And all we are doing is providing the inputs. We're giving the score file, the genotypes, the sample sheet, and we're calling this command here. In the example, in the demo file, the test demo, we're calling this command. And then Nextflow will then pull the pipeline from GitHub, download the required containers, execute the steps, and save the outputs. And so I also want to show you a little bit more about the demo file that we were using for the PGS C calculator, just to make sure that that is working. So as I was showing you, that we were verifying that it works, and just wanted to show you that what was going on behind the scenes inside the log file for it, like when we were downloading Nextflow, just to give you a little bit of intuition. So over here, I can click here and I can go to the log file here. And you can see that it's, downloading a bunch of things. You can scroll down. So now this is where it sees that it is, it's downloading the files using 4 threads. So it's using the curl. This curl is a downloading thing, and it's downloading the Nextflow dependencies. It may require a few seconds. Please wait. So it's downloading Nextflow here. That's what's happening here with this command that we were mentioning. So that's what is happening with the As you see over here, what we are checking out is in this test file, the curl, this bash one. That's what we're seeing over here. That when we're running this one, and then followed by the bash, it's downloading Nextflow. Then we are creating over here these directories and moving Nextflow over there. And then ultimately, we are running PGS calculator, the code here, the test example. So it's just using test. Profile is used to install the workflow and verify the software is working correctly on your system. And the test input data and results are only useful as examples of outputs and are not biologically meaningful. So these are just some of the test information. And it's running it here. It's running. But the Seneca data set, as we're seeing here, it's running, and then it finishes. It succeeded in a minute, 15 seconds, great. And then we can see that it's, running all this here. It's uploading these files. Yeah, and that's what we wanted to test out. So yeah, that's just also showing you like what was happening behind the scenes, as we are running the PGS catalog calculator, like what is happening behind the scenes, and for the command, just to provide some more intuition there. So in this video tutorial, we'll be talking about the Swiss Army knife, the SAK, in the UK Biobank Research Analysis Portal, the RAP. So what is it? The Swiss Army Life, it's a general purpose utility app in the UK Biobank. So when you think about it, I always find these, Swiss Army knives really cool. This one is very intense. It's got a lot of functions. And the way I think about it is it's kind of like, I have this little device here, and it's like a docking port. And what you can do is you can see it has like all the different, ports, HDMI, for VGA cables and whatnot, USB-C, Ethernet cords, and this is a USB connector. It's got all of this as well. So it's multifunctional, and it's got this little plug here that goes right into your computer. So it's just multifunctional. So, I mean, it may not have everything you need, but it kind of works for the most part, which is important. And that's kind of like what a Swiss Army knife does, It's going to have a little bit of everything. It has like knives, a little scissor, even a nail clipper too, which is really cool. A little magnifying glass, a screwdriver, little wrench. I see the nail clipper there. It's like really cool. So it's just a general purpose utility app in the UK Biobank. For most things that you'll need, it's going to have it. So, and these are really cool. Like, the Swiss really designed these awesome Swiss Army knives. I'm kind of obsessed with them. So you can think of it as your workhorse sandbox for quick, flexible analyses without building a custom app. And you know what, my brother once, when he used to be in Boy Scouts and we used to be going around selling popcorn, I would be really excited that if we sold enough, we would be able to win a free little prize pocket knives. That was really exciting when I was a kid, kind of helping him sell his popcorn so that we could rack up the points based on the sales and then buy these little pocket knives, which is really cool. Anyways, just some fun childhood memories. So yeah, it's just a workhorse. It's a sandbox for quick, flexible analysis without building a custom app. And it's available if you go here in the UK Biobank Access Portal. If you go under the under the tools right here. Sorry, if you go under the tools, it'll be right over there. So why it exists? In the research analysis platform in the RAP, many tasks require command line utilities like extracting SNPs, these single nucleotide polymorphisms, filtering samples, converting formats and whatnot. And building a DNA nexus app for every small task is slow and it's just overkill. So the Swiss Army knife, it provides a pre-configured environment with the tools you'll most likely need. So what's inside is it comes preloaded with bioinformatics software. So if you click the tools and you scroll down and you check out the Swiss Army knife, it'll kind of give you more details on what it has, like its Plink2, QC tool, BCF tools, SAM tools, TabX, for, reading different indexed files, R, Python, Unix, Linux utilities, awk, sed, grep, and so on. And it has input and output integration with the research analysis platform, the RAP project storage, and mounted UK Biobank datasets. So you can run single commands or script files, bash, R, Python. And so like typical use cases would be like extracting SNPs from bgen using QC tool, as we'll see. Converting between genotype formats like bgen to VCF to Plink or so on. Going back and forth between them, filtering samples or variants, quality control, QC exclusions, running small data wrangling jobs, joining phenotype files, reshaping tables, quick exploratory stats or plots in R and Python, preparing subsets of data before sending them to heavier pipelines. So the benefits is that it's versatile. It's got so many things it can do. Like in Spy Kids, how that watch could do so many different things, Spy Kids 2, The Island of Lost Dreams. It's time-saving, so it avoids building custom DNA nexus apps. It's cost-efficient, lightweight job. You build only for what you use. It's beginner-friendly, so it's a great starting point to get started on the RAP. So if I had to explain it, too long or didn't read, as they say, It's flexible. If you don't know which app to use, just start with the Swiss Army knife. If I just want to extract snips from a UK biobank BGen file or exclude some participants and output to uplink format, I just say launch the Swiss Army knife, upload my snips that I want or my sample list, and run a QC command inside the Swiss Army knife tool. So yeah, I was mentioning that we tend to use different instances here on the DNA Nexus platform when we're submitting jobs. And so if you go here to the documentation.dnanexus.com, developer API running analyses instance types, to this link over here, you'll be able to find a list of different instances that you can refer to in the dx command when you're running the code to perform your analyses. And it will tell you like how many cores each machine has. You can kind of see what you're getting into. And like, of course, it goes without saying that the more powerful the machine is that you're using, the greater the cost will be for your analysis. Otherwise, we would just all take the most powerful machine, right? So you can see the instance types, the cores, the memory, the storage, and then there'll be some part where it can mention the costs, hopefully. But these are some things that you can note, and you can specify the name in the dx command when you're running it. So some of these might look very familiar, the format, like what is the machine, what is its capability. So these are just for you to keep in mind that this is where you can find that information in case you have to perform very extensive analysis. You can use a more powerful instance type, and you can specify that in the dx command when you're running your bash codes.